Hello, my name is Çağatay Gürel, and I'm a third-year molecular biology and genetics student at Bilkent University. Today, I'm gonna present you my experiment about electromagnetic induction and damping coefficient measurement. The purpose of this experiment is to extend the basic study of electromagnetic induction by measuring the damping effect on falling neodymium magnets through different conductive pipes. The experiment shows that the difference in materials, pipe lengths, and thickness of the pipes affect the induced eddy currents and the resulting braking force. Additionally, terminal velocity is also measured, and the damping coefficient is calculated based on the theoretical and experimental data. The experiment provides a deeper understanding of Lenz's law, Faraday's law, and the role of material conductivity in electromagnetic braking. For the experiment, a 68 cm long copper pipe with a radius of 0.75 cm, a 77 cm long metal pipe with a radius of 0.75 cm, and a 68 cm long copper pipe with the radius of 1.2 cm was used. As a magnet falls through a copper pipe, it disrupts the surrounding magnetic field, which in turn generates eddy currents within the pipe. The eddy currents create a magnetic field that pushes against the motion of the magnet, effectively slowing it down. This is explained by Faraday's law of electromagnetic induction, which states that a change in the magnetic field induces an electromotive force in a conductor. In this experiment, as the magnet falls, the magnetic field around it fluctuates, causing eddy currents to form inside the copper pipe. According to Lenz's law, these currents flow in such a way that they oppose the very motion that created them. Essentially, the copper pipe generates a magnetic resistance that acts against the falling magnet. The graph shows the terminal velocity and pipe material relationship between aluminum pipes and metal pipes. As it can be seen from the graph, the terminal velocity is significantly higher in the metal pipe compared to the copper pipe. This stems from the electrical conductivity of steel being lower than of copper, which results in weaker eddy currents and hence weaker electromagnetic braking forces. Even though their lengths are not the same, this difference does not lead to any changes in the results due to the calculations using terminal velocity. This graph shows the relationship between the damping coefficient and pipe radius. Only aluminum pipes were compared to isolate the effect of radius. This figure shows that the damping coefficient decreases as the radius of the pipe increases. A larger radius leads to the magnetic field and the induced currents being spread to a larger area, in which the braking forces become weaker. The relationship between the damping coefficients and pipe radius is not a linear relation, but the graph is prepared assuming it is due to the values being really small.